So welcome back. So we'll continue. How many of you are having dreams with equations? Dreams and equations in dreams? No? Okay. I don't know if you will call them dreams or nightmares, but hopefully things are seeping into your mind. Equations are now part of your life. Huh? Okay, so today, as I promised, we will talk about evolutionary dynamics. So before I start, so some people were asking some general questions yesterday. You know, how do we sort of build a better handle on building mathematical models and also analyzing them? There is only one answer: practice, lots of practice, and to sort of understand a given model better. One way you can always do is, teach somebody what you have learned, and then the other person will tell you what you don't know. Okay, that's always one really great way to understand, I think, any topic, not just mathematical models, but I think it's probably particularly true for mathematics in general. Without practice, without really working out, it's hard to know how much we really understand. Okay, so to basically practice and teach, so this combination, and broadly discussions, not just teaching, discussions. Those are the really two ways to better handle and be confident about your skills. Okay, so with that short note, so let's now talk about evolutionary dynamics. So since we are sort of making a sort of a jump from ecology to evolution, so let's just quickly recap most things that you already know, and then build upon what you already know. So what are the key processes that drive evolution? Okay, what is evolution? Evolution is basically change in the allele frequencies over generations, right? So what are the key processes that drive evolution? Okay, two processes. Okay, so when somebody asks this question, distinguish two things. One is, what are the processes, what are the ingredients necessary for the process to act? They're not same. Okay. For example, mutations, variations, they're all ingredients that will help you, because in the absence of them, you may not be able to see the consequence of evolution. Okay. So the key processes would be random, genetic drift. This arises largely because populations are not infinitely large in any natural population. The second one is selection. And let's say now, so I'm to a large extent, I'm going to focus on selection in this talk, not random genetic drift, which is what I think Kavita will cover in a lot more detail as well. So think of selection. What are the ingredients necessary for selection to act? When I say selection to act, how will selection cause, changes in allele frequencies? What are the necessary ingredients for it? So let us say that, variation in what? So you want variation in? So variation in traits. Are traits, alleles, okay? And by the way, another question always to keep thinking throughout your life, if you are working in evolution, is what is the unit of selection? It's actually a very confusing, there is no easy answer to this question. Always keep asking yourself, what is the right unit of selection? Is it alleles, is it genes, is it genome, is it individual, is it group? Okay, keep thinking about this. To a large extent, individual as an unit of selection works pretty well. Okay, so alleles are the things that change over time at the population, but in the absence of individuals, alleles cannot exist. Okay, so that's a fairly good answer. If if you have to pick one answer, I would at least pick individual as the unit of selection. But there are some people differ slightly on this. Where exactly is that? I know a boundary. Maybe there is no boundary, but do keep thinking about this. So variation, and the reason why I often prefer traits is that eventually it's possible that there are many alleles, but they all have same phenotype. It makes again. Does it make a difference? A lot of different alleles, but all of them have same phenotype. And fitness happens because of. Fitness is entirely because of the phenotypes of individuals, right? So then that's why I often prefer to say traits, not just variations in alleles. You may have lots of variations, but they all give rise to the same trait. Actually makes no difference. Okay. So variation in traits. What else do you need? Okay, heritability. Okay. Heritability of the traits. What else do you need for selection to act? Okay, differential fitness. So if we have these three, evolution is possible. Okay, evolution by selection certainly can happen. Is that right? Evolution can happen even in the absence of three in finite populations. Is that right? As long as there are variations in traits, you can still have evolution, even without differential fitness. But that is not what I will be covering today. So I'll focus on instances when basically population size is again large. Therefore, we do need this. Okay, so now let us say selection is acting on a population that has these three components. So let's say we go back to measuring allele frequencies. Let us say there is a mapping between alleles and phenotypes. Let's say P represents frequency of some allele A, and Q represents that of P, which is equal to 1 minus P. What do we want to know? We want to know what is the rate of change of this allele frequency. Okay, we want to know this. Is that right? Okay. So in the population dynamics, we wanted to know how population size changes. Here we are focusing on the relative frequencies of two alleles. By the way, the word frequency is a funny usage. Only in, I think, population genetics literature, frequency is used to mean a number between 0 and 1. Okay. But typically, frequency starts with a number of things, number of occurrences of a given thing, meaning it's often a discrete number, 0, 1, 2, 3. It's not a. So technically, proportion is a more accurate word, but in population genetics, frequency is used to mean proportions. Okay. So P can vary only between 0 and 1. Okay. So this delta P depends on what now? This change in allele frequencies depends on. So if I have to calculate this, what will this roughly depend on? Differential fitness and variations in traits. All of you agree with this? Okay. So what is differential fitness between alleles? That would be nothing but is it right? So basically the change in allele frequencies will be proportional to this quantity. All of you agree with this? That's for the condition necessary for selection to act. Yeah. Ratio. What would that ratio be? It's differential fitness. Yeah. Do you have a quick answer for that?
So actually, this continuous time, you take the Malthusian fitness, which is the difference. What you are saying is the Wrightian fitness.
That's where the ratio. Yeah, like in the discrete time models versus continuous time models. But Yeah, thank you for the quick clarification. Okay. So, so you're familiar with the Malthusian fitness and the Wrightian fitness. So we haven't defined these quantities at all, sorry. But if you're looking at the discrete time dynamics, remember the parameter capital R? That's the Wrightian fitness, where you look at the ratio of two population sizes. Okay, and in the context of values, it becomes ratio of two fitnesses. Okay, of two traits. In the context of Malthusian fitness, remember again the small r that I used in the continuous time notations. And that's called Malthusian fitness. Now, all of you do recognize yesterday that you can go back and forth between continuous time model and discrete time model by discretizing the continuous time model, right? As long as the discretization is valid. Therefore, there must be some relationship between capital R and small r. And that is basically R is this. So if this is the ratio of the fitness, then R becomes basically, ratio of the logarithm of fitness 1 minus logarithm of the fitness other, right? So effectively it's the differences that matters. Okay. And what else did we say? Heritability is sort of implicit. Otherwise, I wouldn't even be writing this equation, right? The change in allele frequencies. So this has to be present for me to be even writing this as an equation. What is variation in traits? What's the mathematical quantity that captures variation in traits? Variation of any type. Heterozygosity, that's correct, but much simpler is what I'm asking. What's the simplest mathematical quantity that captures variation in anything? Variance, okay. Okay, all of you agree that. So basically, this delta P, if your statements are all right, this delta P must depend on variation in the types of alleles you have, right? So let us use a notation here, by the way. Let's use a notation Zi to indicate 1 if it's an allele A, 0 to indicate if it's an allele B. Okay? So therefore, average of this Z, so basically Z you can think of as the trait, a mathematical quantity capturing the trait. I have arbitrarily said 1, 0. I could have done the exact opposite also. So what will be the average value of Z in the entire population? Average of Z will be proportion of individuals with allele A, right? Which is same as P. So if I use this notation, P is nothing but average of Zi. Is that right? If I take Z of every individual and divide it by total population size, that will be P. Is that right? Because that will be the proportion of A's in the population. All of you agree with this? Not everyone seems very convinced. No? So Z, let's say that because these are discrete traits, right? So imagine, in fact, I think it's easier to do it for a continuous case. My argument is actually a bit easy for continuous case. Let me just do it that way. So let's not worry about the alleles right now, because I want to make a very general point about any evolution by natural selection, not just the case of discrete, traits. Let's think of a quantitative trait, Z. Z could be, for example, basically quantitative trait of an individual I. Okay? It could be, for example, height of an individual. It could be, any quantitative trait. It could also be discrete trait. Nothing that stops it from being a discrete trait, but it could be any trait that you can put a number, beak size of a bird, or the wing size, anything that has potential fitness consequence that's heritable. Yeah. Yes. So in this case, if I think of quantitative traits, I don't really care if it's one allele is causing a specific trait here. As I said, that evolution can be defined entirely in the trait space. I don't even have to worry about alleles because the selection is acting on traits. Yes. Okay. Is that fine? So let's not even worry about the alleles right now because the general formation is actually easier to understand. Okay. So zeta is any trait. It would be beak size, height of individuals, wingspan, how fast I can run. It could be any of those measures. Okay. It's a heritable trait, is our assumption. And so what will be the average of this trait in the population? It's denoted by Z bar. Okay. So if there is selection on this trait, what should happen? This average trait will change in the population. All of you agree with that? Okay. So we want to understand how does this average trait change? Okay. And you have just told me that it depends on two factors. There has to be differential fitness of traits. There has to be variation in traits. Let us understand these two in a graphical way. Okay. Let us say x-axis is the measure of trait, y-axis is the associated fitness. Okay. So imagine a scenario when the relationship is this. Will you have a evolution? Will you have evolution? Meaning every possible trait has exactly same fitness. Will you have evolution? No. Imagine a scenario like this. Will you have evolution? You will have evolution, right? Okay. So now consider this is case 1, case 2. Consider this case now. Case 3. 2 has evolution. All of you agree? 3 will also have evolution. Which of them will have more evolution? 3. Huh? First has most evolution. This has the faster evolution, right? Okay. So this delta Z therefore depends on slope of this line. All of you agree? Okay. So this is proportional to, let's call the slope by beta, which is basically slope between W and Z. Fitness and the trait. Okay. And consider another extreme where all the traits are like this. Meaning every trait, everyone has same trait. But of course, I really don't care. The actual relation doesn't even matter. Imagine that everybody has the same trait. Then again, will there be evolution? No. Many, yeah, true. I mean, it's a hypothetical thing. That's not necessarily even, doesn't have to be even true. But the main idea I'm trying to say is that everybody has same trait. Will there be evolution in that case? No. So compare to this and this, which will have more evolution? This will have more evolution, right? Why so? Because there is no variation in Z. And we have all said that the variation in traits are actually important. So this quantity is also proportional to, all of you agree that the simplest measure of variation is variance, right? Okay. So if I combine these two factors, what do I get? Yeah. Not quite. Slope is infinity here. It doesn't capture variation. The variation depends on how long this axis is. I mean, I can have this, imagine I can actually stretch this here, stretch this there to make the variation same, right? The slope doesn't capture the variation. Variation is an independent quantity that's actually present, huh? It's just a notation to indicate the slope of the line, slope of the relationship between W and Z. You can even, if you don't like this, you can even skip this. It's not very important. The way, for the current discussions, it doesn't really matter. As long as, the slope is given, beta, it's fine. I didn't say minimum variation is variance. The simplest quantity that captures variation is variance. Is that fine? So is it therefore reasonable to say that the rate of change of the trait because of selection is a product of the slope of the relationship between W fitness and the trait? This captures differential fitness and the variation in traits. Is that fine? Okay. And in fact, there is a constant factor here. In fact, this is defined for so basically, if you now do a more careful mathematical derivation of the same, you will find that there is also a factor of average population fitness here. Okay. And there are some extra terms that occur. Okay. There are extra terms that occur because the heritability is not perfect. Parents and offspring differ for a bunch of reasons. Okay. But nevertheless, the general form of the expression, so I won't write the extra term because I haven't derived it anyway very carefully. But to a good approximation, the rate of change of a trait is given by variance in the trait times the differential fitness calculated as the slope of the relationship between omega and z divided by the average population fitness. And this is also called price equation. Yeah. That's an assumption that we're making here. I don't know. I mean, I don't even understand the question entirely. The question.
It's not been defined in any of the lectures. Have we defined it? I think maybe. So I'm not sure. Heritability is this object called h square, which comes in Breeder's equation, right? So does anybody know what's h square? How much it is? How do you find it? There's some clues over there. It's the genetic variance divided by genetic variance plus environmental variance. Okay, that's what we call heritability. It's something which you can measure. So from the slopes, etc. I think Uma had sort of mentioned that. So that's not what you mean here.
Yeah. I'm not meaning that. No, I'm not.
That's not heritability.
I'm not using heritability explicitly anywhere in this.
No, not even in this expression. You don't have
that
h squared thing, right?
I'm not using that.
Okay, so something.
It's possible to make connections to the Breeder equation from here. Yes. So these are also called the environmental factors that change the allele, the trait frequencies, and the weight traits are changing broadly. And again, I'm not writing that term because it requires more justification, which I don't want to get into. Okay. Yeah, you have a question. Again, I'm not providing a mathematical proof. I said that if you were to do a more careful proof, the constant of proportionality will be 1 over omega bar. Again, I'm not providing a proof. But I think in Kavita's derivation, you'll actually find we'll do the discrete one or the continuous one. But okay, now how do we connect? So does it make sense intuitively at least these two terms? Of course, I understand I cannot explain every term without doing actual derivation, right? But intuitively it makes sense so far. It's a variation in the traits times this and times the differential fitness, both quantified in very, very simple ways. Yeah. Yeah, that's precisely where I'm getting to, yes. In this derivation, so now how do you define an environment here is not very clear, right? So what constitutes an environment? So we have to define that carefully first and then only do these things. You can assume anything and these terms will just keep on changing. Yeah. In fact, it is defined as selection pressure. So I think it's not called selection pressure technique, it's called selection coefficient. That's what I think people call, yeah. And variance of Zi is called potential for opportunity for selection. Because in the absence of that opportunity, there can be no selection. And variance in the fitness is called, I think, another funny term, very similar term. I think opportunity for selection. I forget, I'm sorry. There's actually even a paper that describes many of these terms in an intuitive way. Yeah. Okay. But I'm not, my intention is to just provide a very brief intuitive overview, because with this it helps us make one more step now. So now let us consider the case when Z is a discrete rate, 0 and 1. Okay. Okay, if Z is a discrete rate, now Zi, I'm going back to the one that I wrote in the beginning, is I will denote this as 1 or 0, meaning presence or absence of an allele. Or it could be, an eye color of black will be called 1, blue will be, let's say, 0, and so on, So if I do this, if I do an average of Z, what do I get? Let's say we are thinking of eye colors of all of us here, black versus blue. If I represent 1 as the black eye color, okay, 0 as a brown eye color, so all of us get either 1s or 0s depending on whether we had a black eye color or a brown eye, right? So we'll all either have 1s or 0s. If I add all of those numbers and divide by total number of us here, what would be that number? Proportion of individuals with the black eye color, right? Okay, so average Z now becomes basically P. Is that correct? So we can take this continuous straight case to a discrete case, the way typically you do simple genetics. In that case, what happens to the left-hand side? It's a change in the allele frequency. Okay, that's given by variance in Zi, okay, times. Now what happens to this graph now, by the way? There is no continuous axis anymore. We have only two values, 1 and 0. Let us say this was omega A. Sorry, this is omega B, right? Because 0 represents B. This was omega A. What will be the slope joining two lines? It will be proportional to omega A minus omega B. Is that right? So the slope will be proportional. Again, I'm not. My aim is to not get all the constant factors right. By the way, my intention is to only get the the formula right up to a proportionality constant. Okay. Because somebody asked me yesterday, can you give an intuitive explanation for what I wrote? So this is clear now. But what is variance of Zi? So for those who know something about discrete random variables, if we have 1s and 0s, if the proportion is P in the population, what's the variance of that random variable? It's nothing but P into 1 minus P. So this is something you have to trust me and accept that the variance in the trait for a discrete case basically is product of P into 1 minus P, which is precisely the equation for evolution of allele frequencies. Yes. But it could be anything that actually goes from one generation to the next generation. It doesn't have to be phenotype. It could be anything. As I said, it could be anything that goes from one generation to next. It could be phenotype, it could be an allele, it could be anything that goes from one generation to another generation. It doesn't have to be a phenotype only. So I said, again, you need to know a little bit of mathematics for this. Yeah. So if you have discrete random variables, zeros and ones, and if the average proportion of, let's say, ones is P, the variance of the random variable will be P into 1 minus P. Oh yeah, if you have done the binomial distribution, it's exactly that, huh? Okay, but you have a factor of n also, as a prefactor there. So you have done binomial distribution on Monday, right? Do you remember the expression for the mean and variance of binomial distributions? Did you cover? Was it covered? So what's the mean? It's np, and what's the variance? It's np into 1 minus p. So here n is irrelevant because I don't care about the population size. So it actually becomes p into 1 minus p. It's exactly that. Okay. So basically, if you were to now ask what in this expression, what does P into 1 minus P mean? It's capturing the variance in allele frequencies in the population. In the absence of which there will be no evolution. It again makes sense. P is equal to 0, the variance becomes 0, therefore there is no evolution. Even if there was a differential fitness. P is equal to 1, there is no variation in allele frequencies. Therefore again the evolution will be 0, because even if there was a differential fitness. And the evolution is maximum when the variance is maximum, which happens when P is equal to half, which is the heterozygous case. And in fact, what is P into 1 minus P? It's actually PQ. So in fact, another way of thinking about it is, for this simple 2 allele case, the variance in the traits is nothing but the heterozygosity, which is proportional to heterozygosity, which is basically 2PQ. But again, as I'm not worrying about the constants here, so PQ. Okay. So to me, what's very interesting is the following. Okay. So these are verbal statements of what drives evolution via selection, right? But the simplest mathematical quantities that capture variance and differential fitness actually are also exact expressions driving the evolution. So because when we wrote this, it could have been proportional to beta square. There was nothing that stopped it from being beta square, right? It could have been variance square or square root of maybe standard deviation instead of variance. So, but somewhat surprisingly and remarkably, if you were to do the careful algebra, you will find that the simplest quantities that you can think of are actually also the exact mathematical quantities. Okay. So I did all this because somebody asked me, can you give me an intuitive explanation? I hope I haven't made the life more difficult by this. Is that fine? Okay. So as I mentioned, now we will move on to understanding this part. I quickly explained yesterday how if omega A was always greater than omega B, we'll end up with P is equal to 1, right? With the final outcome, everybody will have allele A in that case. Conversely, if omega B was greater than omega A for all P's, then P becomes 0 because this will be negative, and the simple stability analysis also this will lead to fixation of P, right? Okay. So that much we know now. So I won't do more of pop gen related stuff. Now all of that, either P goes to 1 or 0, necessarily depends on the fact that this has a constant sign throughout. Okay. Now I will introduce some contexts in evolution and ecology where that's not always true. Okay. And there are many nice examples of that, and I'm going to discuss one scenario called animal conflicts. Okay, so we discussed in our population models that animals compete for resources, right? But we also discussed how animals may also cooperate for resources. Okay, so this is one such scenario. Let us think of a scenario where there are some resources. There is a huge landscape, there is some patch of resource. Two individuals, A, let's call them A and B, arrive here. Let's say the value of the resource is V. Okay? Yeah. You have to switch on the mic, please. Switch on the mic, please.
So when you said animals, they get into conflicts and they also cooperate. So it might be a silly question, but which one is more likely to happen?
Yeah, that's precisely what I'm going to discuss now.
Okay.
Okay. What do you think is more likely to happen? Can you please answer? What do you think is more likely to happen? Okay, we'll see. So value of resource, let's say, is V. except that this resource is available to only one individual of the two. They both can't have it. Okay. So they have to give up if they come. They well, actually, actually possible. Sorry, I made a mistake. Let me just modify the story a little bit. So it is actually there are two ways now it can happen. Okay, if let's say both A and B are sort of peace-loving individuals. So what will they do in that case? They will share the resources. What will each of them get? Let's imagine a case, they love conflicts. They like to fight. Okay. So what happens in that case? What could happen in the case of fighting? One of them will win, probably. Other loses. So what happens to the winner in this case? Gets the whole resource. What happens to the loser? 0. Is that it? You made an assumption when you said it is 0. It assumes no cost to fighting. Okay. Is that true? In terms of resources, the gain is this much. Okay. So this is the resource that this fellow got, this fellow got. But in the process of fighting, is it possible that some injuries happen to the loser? That's why that fellow actually ran away. Otherwise, why would you run away, right? I will still go and gather the food, right? So fighting will cause one harm to somebody. Let's not worry about the energetic costs. Let's say one of them injured the other, and therefore that fellow lost and ran away. Okay, in that case, what do you think will happen? That's possible. Let's assume that they are, equal sharers. That just makes mathematics slightly more complicated, but it's entirely possible to incorporate it. Yes. Okay. So in that case, what happens? In terms of resources, you're right. What about the cost part of it? So this fellow injured that fellow. So this fellow paid no cost. Let's assume this fellow paid some cost, right? So what's the net gain in that case? V. This will be minus C. Is that right? So I'm assuming this fellow injured, that's why that fellow ran. I mean, that's also another thing one can do. This fellow also paid a cost. Both of them got slightly, but then it's not very clear why this fellow ran away. Okay. So you can, now what should you do? Should you fight to get the, so now you imagine you can do two things. When you meet a friend, you can share and get V by 2. On the other hand, I take the risk of fighting. Why is it a risk? Because I might lose and end up getting injured and get nothing. In fact, I actually will go back hurt. On the other hand, there's also a possibility that I actually will get the entire resource of myself. So what would you do now? Yeah? Yes.
So if there are chances that the organism can get food from somewhere else.
Yeah, this is the only food they have, unfortunately.
Okay, so then I think they should fight.
Fight, okay. Yeah. You choose to be, I mean, you can choose between the two. Do you want to be a fighter or do you want to be peace-loving? So imagine if there are two alleles. One allele codes for peace-loving individuals, other allele for fighting. Okay. Huh? Absolutely. Yes, a very good point. Okay. So this implicitly assumed that both were fighters and this happened. What happens in another case when a fighter meets a peace-loving guy? Huh? Peace-loving will just won't even fight, right? Okay. And in fact, there is in that case, this fellow will get V, this fellow will get 0 in that case. So you remember, so if there are two types, so there are now, how many possible interactions are there? 4 possible interactions are there, right? Okay, so in fact, there are, people have given some standard names for these things. So the fighters are called hawks, and peace-loving individuals are called doves, okay? So what are the possibilities now? What are the possibilities of pairwise interactions? Hawk can meet a hawk, dove can meet a dove, and the opposite, right? So we often write this in the form of a matrix. Okay, so this is the focal individual of interest, and whatever we write here basically is this net benefit, net gain at the end of the fighting, at the end of interactions. Okay, for the focal individual, I'm going to write this for the focal individual. So can you all now tell me what happens if a hawk meets a hawk? What will hawk gain by that? So yeah. So is everyone clear? Or he suggests that it's V minus C by 2 because I am assuming what you're saying is that when hawk meets a hawk, one of the hawks will win, the other will lose. Okay, but there's only half chance of the focal hawk winning the game, winning the fight. Therefore, so V minus C is the probability of winning is half, probability of losing is half. So the net gain is half times V minus C. Is it clear to everyone? Huh? Okay, there are small variations you can, the way you write these exact terms here, it depends on exact assumptions we make about the fighting. So there could be small variations. So but none of them really change how the results eventually happen. Okay, you have a question? You raised your half hand. Okay. That's one way of looking at it. Yes, we will do that. Yes. Once we write down this, we will look at what is optimum. Yes, we will do that. Another way of, how do we connect back to this? P is the proportion of hawks and Q is the proportion of doves. What will population eventually contain? That's the question we are trying to understand. Okay. Okay. And then we can also then ask in this process, are they utilizing resources optimally? Okay. So this is, now what happens if a hawk meets a dove? What happens to hawk? Gets all the resources because dove, just gives away. Is that right? There is no, it happens to probability 1. And now what happens if a dove meets a hawk? What will dove get? 0. What happens if dove meets a dove? 3 by 2. Excellent. Great. Yeah. Say that again, sorry. Only if dove fights, but by dove by definition doesn't fight, just runs away. It's possible to redefine your dove that way, and that becomes a different type of. So these are also called games, by the way. These kind of animal conflicts are all called games, inspired by the game theory literature. Okay, and this is also called a payoff matrix. So payoff is basically what I call net gain here. Yeah. 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 Dove and hawk. Why? That means, sometimes dove runs away, sometimes hawk runs away. Is that what you mean? Which one? Sorry, which one? Sorry. This one. Yeah. Outcomes. Yeah. This one. Dove gets always 0, right? Because dove always just runs away the moment the fight is initiated. So, it's an assumption I'm making. So the assumption I'm making is, if a hawk and a dove meet, the fight is initiated by hawk, right? What happens to a dove then? Oh, okay, this guy's going to fight, I'm going to run. So he takes all the resource and this fellow runs. On the other hand, in this case, both start the fight. Okay, now my hawk winning is only, the focal hawk, not my hawk. Focal hawk winning is the chance of it are half, and losing are half. Therefore, the net benefit will be V minus C by half times half. But all of you understand how this term came, right? So what we have really done is, probability of winning is half multiplied by the associated payoff minus the probability of losing is half times the associated payoff. Because there are two possible outcomes for the focal hawk here, but there's only one possible outcome for the dove here. Is that fine? Okay. So all of you understand this now. Now let's go back to this equation. To understand whether A will take over or B will take over, what do we need to find? See, this part of the formula doesn't change, right? How the allele frequencies change. Now instead of alleles here, I have to interpret this proportion of hawks and doves. Okay. So what do I need to compute? Basically, this difference for given the set of interactions. Okay. So shall we now basically calculate omega of hawks and omega of doves? How much time do we have? Okay, we have enough time. So all of you understand how this connects back to this, right? So if I understand this term, I can now make a prediction whether everybody will be a hawk, everybody will be a dove. And somebody said conflicts will always win, therefore everybody must be hawk, right? Okay. So what is this now? What is the average? So what is omega h, by the way? It's basically average fitness of hawks. How do you calculate this? Why do you want to assume that? Okay. Okay. He's right. So if you assume that currently hawks and doves are equal in numbers, I just add these two and divide them by 2. That will give me the average hawk fitness. By the way, so what we have written is something called a payoff matrix. So the assumption we now make is that the fitness of individuals is proportional to the payoffs in the games. Okay. And in fact, what people also write is something called a baseline fitness plus the associated payoffs. Why is this baseline important? So an animal in life does so many things. It eats at many, many different places, not only in this patch, right? It has fitness arising because of conflict in mates. It has fitness arising because of, many, many, many components beyond this simple hog-dove game that's happening between two individuals. So to account for all of that together, we write a term called omega 0. Everything else in life is omega 0. And there is some contribution of this specific interaction that's happening. Okay. So now we have to basically, so he suggested that if they were equal in number, I can just add them up and divide by 2. What if they were not in equal number? Let's say P is a proportion of hawks and Q is the proportion of doves. Then what will the average fitness be? P into this term, right? Because a given hawk has a probability P of interacting with a hawk. P into this term. And then probability that a hawk will meet a dove is proportional to frequency of doves, which is Q, which is nothing but 1 minus P, times. Is that correct? So can we simplify this? Has somebody simplified this? V by 2. Sorry? V plus C. This is P by 2, right? Is that right? Huh? All of you got this? Okay, excellent. Now what about, can we do something similar for doves? So we have they also have a baseline fitness. Let us assume that it is same as what's there for hawks. Okay. And then then probability of dove interacting with the hawk is P, but that's multiplied by 0. Probability of a dove interacting with dove is 1 minus P multiplied by V over 2. Okay. Can you now tell me which of them is greater, the hawk's payoff, hawk's fitness or the dove's fitness? Anyway, this is not, this term is 0, therefore this becomes omega 0 plus 1 minus P V by 2. Huh? So let us compare these two. Let's compute omega h minus omega d. Okay. When you do this, the omega zeros cancel out. Okay. So you have this V that remains as it is, V minus PV by 2 minus PC by 2 minus of 1 minus P into V by 2. Is that clear? By the way, this time is nothing but minus V by 2 plus PV by 2, right? And this cancel with this. Okay. This minus this will give me V over 2 minus PC over 2. Which is basically half times V minus PC. Or was everyone able to get the same expression as I have? Is the mic working fine? Okay. So you remember yesterday I asked the question, does omega A minus omega B depend on P? I think several of you said no. I think a majority of you said no. Are you happy to change your opinion now? Yesterday I asked the question in this equation, does this term depend on P? I think the majority response then was it doesn't depend on P. Or you will, and under that case, whether it was positive or negative, gave us the result of P is equal to 1 or 0. Right? Now, all of you are willing to revise your opinions now on whether this depends on P or not. So, whenever we have this omega A minus omega P dependent on P, it can lead to a type of selection called frequency dependent selection. Why do we call that? The selection coefficient basically, you know, if you go back to the derivation, this is basically beta, right? In the simplest sense, the differential fitness, right? This depends on the frequency of the two alleles. So the fitness of an allele basically, or rather relative fitness between two alleles, depends on the frequency of the alleles themselves. Right? Because it depends on P. And this can lead to a situation which is not obvious from comparing their fitnesses at low frequencies, for example. So this can lead to a very different outcome than compared to a case of this is entirely being independent of P. Okay. So anyway, so we'll just see in this case, let's see what happens. Okay. So now we can go back to that equation, right? We can plug that there and we can solve all the stability analysis. Okay, is that right? So what's the new equilibrium that's now possible, by the way? If I plug this back here, what do we have? It's V minus PC, right? So the three equilibrium are P is equal to 1, P is equal to 0, and this term is equal to 0, which means P is equal to V divided by C. So we have a possibility of a new equilibrium now. So when the evolution stops, whenever the two alleles have same fitness, right? Another way of thinking about it now. And that can happen when V is equal to PC. Is that fine? Yeah. Which this fighting, you mean? In this case, because of fighting. Absolutely, yes, yes. Is it always the case that the lack of cost will? I don't know if such a general statement can be made, but in this specific case, probably you're right. I mean, that's very evident, in fact. You know, in this specific case, if this cost was not there, of course, this would just be half V, which means the Hawks will always be better off than Dows. Okay. Therefore, the outcome will be that Hawks will win the game. Hawks will take over. Yeah. I will discuss that point in a bit. I'll come back to that point in a very shortly. Huh? Yeah. So imagine a case when this did not depend on P. You had only 0 and 1. Allele A fully taking over or B fully taking over. But now when this depends on P, an intermediate P between 0 and 1 is also possible whenever that term is equal to 0, right? And that is happening only because the fitness depends on the frequencies themselves. Yeah. Now what is W by C mean V by C? We'll go to 1. Okay, we'll find all the outcomes. The first thing I want to convey to all of you is now, you know, there is now a possibility of a new equilibrium. Is that clear to everyone? Do all of you agree with that? Let's just agree, then we'll find out the consequences very soon. Yes. Yes. Absolutely. Yes. We'll come to all of the. I think you're already jumping ahead of what I'm thinking, which is really great, by the way. I'm really happy that all of you are doing this. Okay. But all of you acknowledge there is a possibility of a new equilibrium. So we'll now consider this equilibrium, understand when is this valid, does it make sense, and many of you have already given answers for this. Huh? Okay. Yeah. So now let us understand this new equilibrium. Yeah. Thanks. Let us understand this better now. The first and foremost, as we pointed out, is that since P is a frequency which is between 0 and 1, this cannot be greater than 1. Which necessarily means this equilibrium is meaningful only if V is less than C. Okay. If V is greater than C, what happens? If V is greater than C, what happens? P will become greater than 1. Therefore, this equilibrium doesn't even exist in biological sense. Look at this equation in that case. If P is greater than V by C, what happens to this? Huh? Huh? Or, other way of thinking about it, imagine a case when V is greater than C. Okay, let's consider case 1. The most, in some sense, a very trivial case. V is greater than C, which is when this new equilibrium P star, let's call this P star, will be greater than 1. But let's understand what does it mean to omega h minus omega d. This implies omega h minus omega d is equal to half v minus pc. P is always less than 1, right? So the maximum value of this is v minus c. This is always greater than v minus c. Is that right? Because the maximum value of p is 1, which means that if v is greater than c, this is greater than 0. Okay? Which means that Hawks will always be better than doves. Which means that the proportion of Hawks will eventually become 1. And in some sense, going back to your question, somebody said this frequency dependence is true only when there is a cost. Okay. In fact, there is even a stronger statement you can make. That frequency dependence will have an effect on the result only when this condition is not true. See, as long as v is greater, even if there is a cost, if v is greater than c, omega h will be greater than omega d, therefore Hawks will win. So the alleles that code for Hawk behavior will undergo fixation. Yeah, as long as the benefits of resources is more than the cost of injury, then it's always good to fight. Okay? Which is also, I think, what one student did predicted, I think. I think conflict will always win, not sharing, right? Okay, now let's understand this, an interesting aspect of this. Let us consider two hypothetical cases. If everyone was Hawk, if this outcome of this, of course, if all Hawks, right? If everyone was Hawk, what's the average fitness in the population? What will be this? It's basically v minus c divided by 2. Everybody is Hawk, right? Consider another scenario if all are doves. What will be the fitness? V by 2? Now, do you have any comments on this observation? So, if everybody is dove, the average fitness is equal to v by 2, which is greater than the fitness of individuals when everybody is a Hawk. But what did evolution do here? Evolution drove everyone to Hawk. Evolution drove towards conflicts, which actually has a lower fitness than everyone being a peace-loving individual. So the common intuition that evolution always makes things better for everyone is therefore not true. Yeah. Hey, but your prediction has come true now. You must be very, very happy. You said conflict will win, which has indeed happened, right? Yeah. Okay. It isn't. Obviously, it isn't. But the general conception. Some people think, oh, if there is a better thing that can happen, that will happen, right? That's the general way we think in the adaptation. Fitness will keep on increasing up to you reach maximum. Yeah. Yeah, I'm not saying they're same. So the question is, will evolution always make everyone fitter? Answer is no. It will in many, many cases, but it also will not in many other cases like this. And this is a very simplest example when that is not true. Huh? Where did I assume there's no variation? Hey, but that's the outcome here. Even if I started off with variation, this is the eventual outcome, right? When population reach fixation, everybody will be a hawk, and then everybody's fitness will be V minus 2. But imagine a hypothetical case of everybody being a dog. They all would have been better off. But that didn't happen. Okay, okay, that's the case one. Now can I write this? Can I write here? Can you all see? So, okay. The next case will be V less than C. In fact, this is true for even this, right? Will this be true for this also? Yeah. Everything should be true for this also, right? No, but only at P is equal to 1, this equality will happen. Right? Because PC. Okay. So now the more interesting case when V is less than C. In which case P star is a number between 0 and 1 now. Right? So now what happens? Okay. So P star actually now is equal to what is that? Sorry, V over C, right? Yeah. V over C, and this number is now between 0 and 1. Now the question will be: will population reach all hawks, all doves, or will they reach an intermediate frequency given by V over C? What do you think is the answer? Can you work this out now? You have learned enough about how to solve the differential equation. Will you be able to work this out? Can you please work that out? That will be really nice. Huh? I mean, in fact, it's now this condition will be very similar to the other model I mentioned yesterday. So you know how to work this out now, right? Basically, in this equation, you substitute V minus PC. Okay, so you have the right hand side f of E. You plot that f of P, identify all the equilibrium, and identify the stability. So you basically need to plot the function. Okay, and then that should tell you whether this equilibrium is the stable equilibrium or not. Please do it. Yes. Yeah. 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 Here is it? See, if this is true, this equality will happen only at P is equal to 1, right? I mean, this equality can happen only at 1. It may never even happen. You know, so consider two cases: V greater than C. This equals to 0 will never happen. Okay. If V is equal to C, the equality will happen only at P is equal to 1. Yeah. It's a very technical question. I will discuss it with you later. Yeah. Done? Great. Are people able to plot? Okay, that's right. So what is this now? Is it stable or unstable? Yeah, so, yeah. So plotting is one, and also find out stability, huh? Identify equilibrium and find if they're stable. Is everyone done? So, I mean, I will just, because we are running out of time, I will just do this for you. So this function will look like this now. 1, 0, and this will be P star, which is V by C. Okay. So if I start with all, so remember that 1 corresponds to all hawks, the way we have defined. 0 corresponds to all doves, huh? Everybody being dove in the population. So imagine that everybody is now a dove, and I add a few hawks. Who has, what happens to the growth rate of hawks? So F is the growth rate of hawks, right? So P represents proportion of hawks, therefore F of P represents how hawks are growing. So what? So is it positive or negative? Hawks will now increase. Okay. So therefore this is an unstable equilibrium. Likewise, if I start at 1, which is all hawks, if I add a few doves, what happens? Hawks will reduce. The growth rate of hawks is negative the moment you add a few doves. Okay. And the intermediate equilibrium, if I add a few hawks here, they will all die. If I add a few doves, they will all die. So this is the stable equilibrium. So in intermediate frequency where both hawks and doves coexist, so in terms of genetics, the alleles that code for hawk behavior and the dove behavior are both present in the population. That's the stable equilibrium. Okay. And again, remember, even in this case, if you were to think of what's the ideal, optimal scenario, everyone must have been still a dove, because this always holds true. The average fitness is always best when everybody is a dove. Okay. But what you now have is an intermediate case, mixture of hawks and doves. Also, another very interesting thing. When actually V is less than C, what happens? V minus C also becomes negative. So everybody here means that they all have basically effectively negative fitness now. Now adding a few doves, therefore, is beneficial for doves, but only to some extent. Okay, and therefore they reach the intermediate equilibrium. So in the afternoon session, I will. So now that I have shown you sort of how to use the mathematical equation framework to come to the evolutionary equilibrium, it turns out that there is a much simpler way, just based on this alone, to understand what might be happening. Just by looking at this payoff matrix, we can argue many interesting possibilities. I will just show you how to do it in the afternoon class.